5.1 is nth roots and rational exponents, and rational exponents just mean fraction exponents, which can be a little bit tricky sometimes, but there's a trick that you can use to rearrange them in radical form, and that usually makes it a little bit easier to evaluate them. So in the upper portion of the screen, you can see this like b raised to the e over r, so we have a fraction exponent. If we want to rearrange it in radical form, the b goes inside the radical, usually like say b for base, and then the e, the numerator from the fraction exponent, becomes the exponent out here, and that can go inside or outside the radical. Usually we put it outside though, it makes it a little bit easier. And then r becomes the like type of radical or root, or you may hear it as the word index. So r ends up being like, if it's a 2, it would create a square root radical. If it's a 3, it would create like a cubed root radical. So yeah, okay. So for example 1, we're just going to rewrite each of these in radical form and then see if we can evaluate them. So for number 1, 25 raised to the 3 halves, the base would be 25. E is the numerator of the fraction, so that's 3. And then r is the denominator of the fraction, so that's 2. So if we rewrite it in radical form, the 25 would go inside the radical. R is telling me what type of radical it becomes, so it'll become a square root. You don't need to put the 2 there, but if you want to, you can. And then after that, we'll raise it to the 3rd power. So now that we've rewritten in radical form, we can just see, okay, I'll take the square root of 25, so that's 5, and then I'll take that 5 and I'll raise it to the 3rd power, which is 5 times 5 times 5, or 125. So 25 to the 3 halves power, rearrange it in radical form, it becomes the square root of 25 cubed. Square root of 25 is 5, 5 to the 3rd power is 125. For number 2, 16 raised to the negative 5/4 power. There's a couple different like orders that you can do this problem in with a negative one, but I'm just gonna go ahead and start with labeling what what B, E, and R are. So B is 16, E is negative 5, R is 4. So the B goes inside the radical, so 16. R is telling me what type of root it is, so it's going to be a 4th root of 16. And then the exponent is negative 5. I'm not going to worry about the negative exponent till the end. We'll just kind of start to evaluate from there. So the 4th root of 16, that's asking what number times itself 4 times equals 16, and that's 2. So 4th root of 16 is 2, raised to the negative 5th power. And then when we have a negative exponent, we have to take the reciprocal of the base. So the base of this exponent is 2 or 2 over 1. The reciprocal of it would be 1/2. So this would flip down here, and this would become 1 over 2 to the 5th. And then 1 over 2 to the 5th becomes 1 over 32. Number 3, 81 to the 3/4. So our B is 81, E is 3, R is 4, so 81 is going inside the radical. It's going to be a 4th root again because R is 4, and then E is the exponent, 3 is the exponent. So like I said, you can put the 3 inside here, but it wouldn't really do that much good because then you'd have to take the 4th root of a bigger number. I think it's easier to take the root first and then use the exponent after. So the 4th root of 81, that's asking what number times itself. 4 times is 81. You can always make like a factor tree for these if you want. So 81 is like 9 times 9, and both 9s are 3 times 3. And it can't be broken down anymore. And I have 4 3s. I'm taking the 4th root of 81, so that means that the 4th root of 81 is 3. And then I still have to raise that to the 3rd power, so 3 times 3 times 3 would be 27. And then number 4, 9 to the negative 1/2 power, so my B would be 9, E is negative 1, R is 2, so rewrite it in radical form. The 9 goes inside the radical. It's a square root because R was 2, and then we're going to raise it to the negative 1st power after. So square root of 9 is just 3, and then to the negative 1st power, we have to simplify a negative exponent. You can't have like a negative exponent in your final answer, so we have to take the reciprocal of the base. That flips this 3 down here, and it becomes 1 over 3 to the 1st power. But 3 to the 1st power is just 3, so final answer 1/3. Okay, example 2, we're just solving, so with different types of roots. So for these problems, they work pretty much the same way as like solving with square roots. It's just we'll use different types of roots as opposed to only a square root to solve them. So number 1, 5x cubed minus 320 equals 0. We still want to isolate the portion that's being raised to the power. So we want to try to get that x cubed by itself. So to do that, I'm going to add over the 320. And then I have 5x cubed equals 320. I have to divide both sides by 5 to get that x cubed by itself. So 320 divided by 5 is 64, so I have x cubed equals 64, and then from there I'm ready to cube root both sides to get x by itself, so it's no longer x cubed. So cube root both sides. If you want, you can like make a factor tree for 64, but it's asking what number times itself 3 times equals 64, which 4 to the third power is 64. So it ended up being x equals 4. And when you have a odd root, so like we're taking a third root, there's only a positive or a negative answer. There's not both. Like traditionally, if you have like say x squared equals 4 and then I square root both sides, I would have to include a plus or minus in front of it. That's only for even roots, so it doesn't work for odd roots. We just have to use the one or the other, because like if I were to say negative 4 was also a solution, well, if I take negative 4 and cube it, it's not positive 64, it's negative 64 because we have 3 negatives multiplied together. Okay, so for any odd root, you just have the positive or negative answer depending on what number was inside your radical. So just x equals 4. Okay, number 2, x plus 3 to the 4th equals 24. The portion that's being raised to the power is already isolated. I can't like subtract that 3 out or anything like that because it's in parentheses to the 4th power. So I'm going to just go ahead and 4th root both sides. That cancels out this power right here. It frees up the x plus 3, and then I'm left with the 4th root of 24. We want to try to simplify it to see where we get. We can make a factor tree for 24, so it'd be 24. I could do, say, 2 times 12, and then 12 I can do 2 times 6. 6 I can do 2 times 3. So I'm at all my prime factors. Since it's a 4th root, I'm looking for 4 of the same number, and I have 3 2s and a 3. So I don't have 4 of the same number, so it just means I can't pull anything outside of my radical, and the 4th root of 24 is already simplified. So because it's a even root, we have to include the plus or minus in front of it, so plus or minus the 4th root of 24, and then from there we just want to get x by itself, so we'll subtract over the 3. So x equals negative 3, and then plus or minus the 4th root of 24. Okay, and then number 3, 1/2 x to the 5th equals 512, so I want to get that x to the 5th by itself so that I can go ahead and cancel it out. To do that, I'm going to multiply both sides by 2 in order to get rid of that 1/2. So 2 times 1/2, that cancels out, and then I have x to the 5th power equals 512 times 2 is 1024. And then now we're ready to 5th root both sides to cancel out that 5th power because those are inverse operations. That frees up the x, leaves me with just like a regular old x to the 1st power, and then I have the 5th root of 1024, so I want to try to simplify that. I'm going to make a factor tree for it. If you don't need to make one, like if you you can guess and check like a bunch of numbers that maybe multiply together to equal 1024, that's fine, but the factor tree just kind of comes in handy like later on in the chapter. So 1024, I'm just going to break it down by like 2s. So it can be 2 and 512, 2 and 256, 2 and 128, 2 and 64, 2 and 32, 2 and 16, 2 and 8, 2 and 4, and then 4 is 2 and 2. So since it's a fifth root, we're looking for 5 of the same number. I have 1, 2, 3, 4, 5 2's right here. And we're just looking at like the prime numbers at the bottom. So basically all the 2's. And then I have 1, 2, 3, 4, 5 2's right there. So since I have a 2 that I can pull out from here, a 2 that I can pull out from here, if you can pull out multiple, you multiply them together. So 2 times 2, 4, and then it was a fifth root and odd root, so I don't have to include the plus or minus. So it'll just be x equals positive 4. When you're taking a odd root, you don't have to do the plus or minus. It's only one or the other, but you can take the odd root of like a negative number. So if this was, say, like the fifth root of negative 1024, this would be x equals negative 4. Because if you take a negative 4 and multiply it by itself 5 times, you'll end up with a negative number, negative 1024. Okay, so next section is just properties of exponents review. You should remember this a little bit from Algebra 1, but if you don't, it's no big deal. We'll treat it like it's the first time we're seeing it. So there's a few different properties. The first one is called the product property. It doesn't really matter if you don't know the specific names. It's just more important that you know how they work. So for the first one, x cubed plus times x to the fourth. So we have two powers that are being multiplied together with the same base. So I'm going to expand these. So I'm going to take x cubed and then expand it into x times x times x. So 3x's multiplied together. And then x to the fourth, if I expand that, it's 4x's being multiplied together. So x times x times x times x times x. I don't know if I said an extra one accidentally. But 3x's multiplied together, and then times another 4x's being multiplied together. All together, I have 7x's being multiplied together. So that kind of leads us to like what we actually do and kind of the shortcuts. You don't have to expand it every single time. When you have two powers that are being multiplied, you just add the exponents. Oops. Okay, so two powers, same exact base, x and x. We can add their exponents as kind of a shortcut. Another example of it is like, let's say I had x squared times x to the 9th power, and I didn't want to write out 2x's followed by another 9x's. I could just add the two powers together. It would become x to the 2 plus 9, or x to the 11th power. Okay, the next one, x cubed to the 4th power, it's called the power of a power. If I were to expand that, this means like x cubed, so 3x's 4 different times. So it would be like x times x times x, that's one of them, times x times x times x, that's another one, times x times x times x, a third one, times x times x times x. So I have x cubed 1, 2, 3, 4 times, and then all together that gives me 12 x's, so that would be x to the 12th power. So the shortcut for that one is to multiply the exponents. So when you have a power raised to like another exponent, you just multiply their exponents together instead of having to expand it. So another example would be if I had, say, x to the 10th power, and then that was being raised to the 5th power. So if I were to expand that, I would have to write x to the 10th 5 times, which would be a lot. But we could just use the shortcut and multiply them together to get x to the 50th power. Okay, the next one is called power of a product, where you have like things that are being multiplied inside the parentheses, and they're both being raised to the being raised to the same exponent. This one kind of works like distributing, but we don't really use that word to describe it. But as long as everything in the parentheses is being multiplied as opposed to like added or subtracted, we can just apply this 4th power to both factors, or to all the factors that there are. If we were going to expand it, it would be x times y 4 times, so xy, 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 and then all together, if I were to kind of count all my x's, because multiplication is commutative, so I can rearrange it if I wanted to. I have 1, 2, 3, 4 x's, so x to the 4th, and then I have 1, 2, 3, 4 y, so I have y to the 4th. So we can achieve that same thing by basically just like taking that exponent, the 4, and applying it to both factors, and it can be more than 2 factors as well. So apply power to each factor. Another example, let's say I have like x y, z, and then that's being raised to the third power, that third power just goes to each factor, which a factor is just something that's being multiplied. So this would become x cubed, y cubed, z cubed. Okay, next one, x to the fourth over x cubed. So this one is like quotient of powers where you have like one divided by the other. So if I were to expand that, I have x times x times x times x over x times x times x. So like 4 x's in the numerator right here, 3 x's in the denominator right here. And then, of course, like if you divide something by itself, it cancels that out, or it's just like 1. So this x cancels out that x, this x cancels out that x, this one cancels out this one, and I'm just left with x to the first power. So when you have a quotient that you're trying to simplify, you subtract the exponents. But it only works if they're the same base, because like x and x in this case, an x divided by another x, those cancel. But if there were different bases, like say this was x to the fourth over y squared, and x doesn't cancel out a y, so there's nothing I can do there. And then another example, let's say I have x to the 10th over x to the 4th. I just have to subtract 10 minus 4, so it would become x to the 6th power. Next one's called power of a quotient, so x over y to the third power. This one works pretty much the same as the power of a product, the one up here, where that exponent just gets applied to like both the numerator and denominator this time. So if I were to expand it, it would just be xy like times itself 3 times, so xy, 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 and then all together I have x times x in the numerator, so x cubed. And then I have y times y times y in the denominator, so y cubed. So that third power just basically got applied to both the numerator and denominator. So for what to do, apply the power to numerator and denominator. Another example would be, let's say I have a over b to the 6th power. That 6th power just gets applied to both. So it would become a to the 6th over b to the 6th. Okay, so next one is a 0 exponent. So let's say I have x to the 0 power. The easiest way to expand or like kind of make sense of this one is to use the quotient property. So I'm going to use the quotient property, the one from right here, to kind of help make sense of x to the 0. So let's say I have x squared over x squared. If I were to use like the shortcut for quotient property, that would tell me that I need to subtract the exponent. So it'd be like x to the 2 minus 2, which is x to the 0. So that's what we're dealing with. But if I were to actually expand the x squared over x squared, it would become x times x over, x times x. Sorry, it's a little crunched in there. But anyways, x times x over x times x, both x's cancel out. And if everything cancels out, I'm not left with 0, I'm left with 1. So anytime you have something raised to the 0 power, it's equal to 1. So that's the shortcut. Anything raised to the 0 power equals 1. And then another example, let's say I had like multiple terms. So let's say 2x, and that whole thing was being raised to the 0 power, even though there's multiple terms in there. Anything that's raised to the 0 power, as long as like both in parentheses, would equal 1. Okay, and then the next one, the negative exponent, so x to the negative 4th power. This one's the easiest to make sense of, like with a table. So I'm going to use, like let's say a power with a base of 3 for the table, just something random. So let's say I have 3 squared, 3 to the first power, 3 to the 0 power, 3 to the negative first power, and then 3 to the negative second power. So we're just like decreasing by a power of 1 each, or by 1 power each time basically. So 3 squared, we know that that's 9. 3 to the first power, we know that's 3. 3 to the 0 power, we just learned that would be 1. So now if we kind of look at the table, we can kind of establish a pattern. So each time, like 9 divided by 3 would be 3. 3 we're dividing out of 3 to equal 1. So every time we go down the bottom row of the table, we're dividing by 3 each time. So we can continue to divide by 3 to figure out what's going on with the rest of our table. So if we divide by 3, 1 divided by 3 is 1/3. And then divide by 3 again. 1/3 divided by 3 is 1/9. So that's why that's why we have to take the reciprocal of the base with negative exponents, because we're essentially like dividing out a power of the base each time, or dividing out the base each time, and it's giving us a smaller and smaller number. So for the trick, we take the reciprocal of the base, or you flip it into the numerator and denominator. There's not a great way to write that or kind of speak it, but I'll give you another example. Let's say I have like x to the negative third power. It flips. So like right now it's in the numerator. I can make it over 1. It's going to flip down to the denominator to become positive. So it'd become x cubed in the denominator. I have to leave something in the numerator. Like I can't just put nothing there. So if there's nothing left, I put a 1. And then another example, let's say I had something that like started off as a fraction, like it was 1 over y to the negative second power, and I had to get a positive exponent. It's going to flip back up. So it can flip in either direction. It's just wherever it starts, it's going to flip to the other side of the fraction. So numerator to denominator, or denominator to numerator, up to down, or down to up. That y to the negative second power moves up, becomes y to the positive second power. And then, I mean, you can write it over 1, but it's not necessary. So basically, moral of the story, if there's a negative exponent, it switches positions. It starts in the numerator, it'll go down to the denominator, or if it starts in the denominator, it'll go up to the numerator.